Let's continue then. And now we try to extend the previous model that was deterministic, because all the data, all the parameters in the model were known in advance. Typically will be, if we, for example, are introducing the demand, we will typically introduce the mean demand or the median demand. If we are introducing the maximum wind power that can be produced, we will introduce, let's say, the most probable, the mode, the median, the mean value, okay? Now we would like to see first what are the effects of some uncertainties in the unit commitment problem. Remember that the unit commitment decide which units to connect now, okay, for tomorrow. So we are deciding from Wednesday until the next Tuesday. This is the usual time scope, 1 week. We are running the model now, but our first decision comes tomorrow. And we need to decide today which units will be started or will be connected tomorrow at 0 hours, okay? And now we want to introduce uncertainties. Which are the kind of uncertainties you think that are relevant in this time domain for the next week? Okay, so one possible uncertainty is the demand. If, as you have said, in winter, if the temperature drops, the demand will increase. In summer, if the temperature increases, the demand will also increase due to the air conditioning. What else?
There could be like regulatory changes, all costs would go up.
I don't know which are the time step for variation of the coal cost, but we can assume that you have in your piles, you have in your jar, you already have your coal and you have paid something. So in this time domain, that is next week, I don't think that the coal cost will change a lot. In the medium term, yes, but not for tomorrow, not for the next 5 or 7 days. Okay, that will be related with, let's say, failure of some units, either by themselves or because of they have lack of gas through the pipelines. What else? Which is the most relevant uncertainty nowadays.
So this, again, it goes back to the sort of weather prediction, how much wind is going to blow next week.
Okay, typically the wind, sun, etc. For high renewables systems, that will be the huge uncertainty. We don't have good predictors for the next 10 days for the wind blowing, and therefore the generation of wind, the generation of the wind power. Okay, these are the topics we want to cover. First, a general description of the wind. Then we will see 3 impacts of the wind in medium and long term, short term, real time, and then we will present briefly the stochastic unit commitment. So which uncertainties we are able to consider in the model in order to hedge our decisions, our commitment decisions that are the main ones we want to take with this kind of models against the uncertainty we are considering. So we may have, for example, this kind of things, okay, as uncertainties for the next week. Something related with the demand, in particular can be the demand response. So, demand response will be something related with the modulation, the variation of the demand of the buildings, of the communities, etc., of the industries, in order to adapt them to, for example, buy that demand at a lower price, the electric vehicle consumption, the data center. We will see in Thursday and Friday, we will see the flexibility of the data centers. And on the generation side, we will have wind power, solar generation, solar CSP or thermal generation, small run of the river, and other type of technologies that will not always be consistent. What are the three or some reasons in order to be able to integrate as much as possible renewable generation? What can be the drivers, the reasons for some countries succeed in this integration? What do you need in order to maximize the integration of renewables?
First thing is how much wind, you have to have good resources. So
Okay, let's assume that you have.
average wind speed should be above specific level.
Okay, we are asking on the other side. So we have plenty of wind, we have plenty of resources, we want to integrate as much as possible. Connected, the network, okay? For example, here, you are connected to Canada, you are connected to the northern side, you are connected to other, in the US, what you call pools, New England Power Pool, etc. Other pools are basically large areas connected among them. So if it's windy here in the northeast coast, you can export to southern part of the US in the east coast or to the central part of the US, etc. So one is this thing and the other? Storage. Okay, so flexibility in general. Flexibility comes from storage, batteries, long duration storage like storage hydro, pumped storage hydro, any kind of storage allows you. Why? Because you are able to save, to keep that energy stored in some location and then to produce later on. And beyond that, typically this pumped storage hydro and batteries are very flexible. So they are very quick reacting to increasing or decreasing the production very quickly. So basically, network and storage flexible technologies are the key drivers for integrating. So for example, here we have the Californian system in 2024, and they have like 62% of renewable generation, okay? Here you have the Spanish system. In 2021, the wind power became the biggest share in producing electricity. And here you have the same values for 2025, where we have, for example, 20% from solar photovoltaic, wind 22%, nuclear 20%, hydro 13%, and only 15% comes from combined cycle gas turbine. So 60%, around 60% is already coming from renewable generation. In Portugal, in the latest year, not the year before 2024, they reached 70%, okay? Remember always the two key points: network connections with their neighbors or in their large areas, and flexibility coming from hydro, batteries, etc. Why the integration of renewables has been so successful? Because of the cheapest or huge decrease in what is called the LCOE, levelized cost of electricity. Basically, when you are buying a wind farm, you pay the cost of the capital cost of the wind farm, and then you are starting producing electricity. So if you divide this capital cost, assuming that there is no variable cost, if you divide the capital cost by the total amount of electricity produced in the next 20, 25 years, etc., you get the LCOE, the levelized cost of electricity. And if you compare this levelized cost of electricity for the different technologies, the installation cost has decreased 87%, 60%, 55%, 50% for solar PV, solar thermal, CSP, concentrated solar power, offshore wind, onshore wind. Okay, so a huge decrease in capital cost, a minor increase or some increase in the capacity factor. The capacity factor is basically the total energy produced divided by the maximum, in theory, energy that can be produced. If we have a 100 megawatts of wind farm, okay, the energy produced in a year divided by 100 100 times 8,700 hours will be the capacity factor. And the capacity factor typically is, the increase in the capacity factor is typically due to performance increasement, efficiency increasement. You are developing a better solar cells, better wind turbine, etc., and therefore they have increased the capacity factor. You are able to capture more wind, so to produce electricity with a wide range of wind speed. And therefore the total LCOE, levelized cost of electricity, has decreased by 90% in 15 years from 2010 up to 2024, 90%, 75%. So that means that they are very competitive. This is the same graph along the time. This corresponds where these savings have been obtained, the share among the different components or, let's say, aspects or type of cost of the different technologies. And this is a comparison of the LCOE with respect for the different technologies. So, for example, we have here between 30 here. So here we have the natural gas combined cycle, something between 34 and $40 per megawatt hour. So that will be the capital cost plus the production cost. It depends on the gas price, okay? So, but they are around these values, let's say 40 euros. Here, for example, we have the range of values for the euros, the dollars per megawatt hour cost of the offshore wind and the solar PV, okay? So solar PV and wind are competing nowadays, depending on the gas price, are competing with the CCGTs in many countries, depending on the countries. Solar CSP, it's higher, and offshore wind is higher, higher LCOE. Sorry.
So if you look at the price difference between maximum and minimum for onshore,
it depends. You see that these values can be for, let's say, different countries, or for even in this country, for the different, let's say, efficiencies of the combined cycle, or the different gas prices. If you are buying, let's say, in Corpus Christi, or you are buying in Texas, or you are buying Louisiana, I don't know.
okay, but still, if you look at, for example, at NGCC, okay, combined cycle, you see the difference between maximum and minimum is $6.
Yes.
For onshore wind, the difference is almost.
Yeah, but but because of the, you can put, let's say, an offshore wind close to the coast with very expensive, let's say, land, or in the middle of the mountains with cheap land, or higher efficiency with high winds or lower winds. So the range, I mean, in theory, you are exploring the most profitable locations. However, once you have exploited all of them, you must create or put wind farms in another locations that have no so much wind.
Yeah, and actually natural gas on the CC, the combined cycles are very modular, very well-known technology, so that's why it's very stable, very powerful. Okay. What I would like to tell is that I guess natural gas with CCS is not considering the cost of developing the pipes for CO2, right? Because it's a bit close in that case. That was
So it's the following one, this one.
And this data is for the whole world, or is this for Europe?
Is made by EPRI, is 2024. I guess it's not for the whole world, probably it's just for the US. This is the decrease in the LCOE depending on the capacity factor. So you have, let's say, a wind farm with, let's say, 50% of the time that can produce at maximum capacity, or another one that is only 35% of the time, then the LCOE, given that you are producing more electricity, will decrease. These values are for the US, cost of wind and cost of solar for the US from the decrease in those the same years, so probably is very similar. This corresponds to who is investing in solar and wind, and you see that China is investing more than the sum of all over the rest of the world. So and you can see that more or less Europe and the US are investing more or less the same in renewable generation. On the left, onshore wind, and on the right, solar PV. These are just maps of the different resources. This is focused in Europe, physical where the wind farms are, and these are the resources on the left. This is the new installations made on every year. The dark blue corresponds to onshore, and the light blue corresponds to offshore. So you can see that there has been a lot of around, let's say, 10 gigawatts of capacity per Europe per year, okay? And we are multiplying by 1 or by 2 for the next years to come, okay? These are the sizes of the wind turbines, okay? The dots corresponds to the sizes. You see this axis, and you can see that for onshore wind the onshore wind turbine, the typical one, has, let's say, 3-4 megawatts. Each turbine produces at most 3-4 megawatts. Offshore wind turbines, if we get again the dots, it's around 9 megawatts. So offshore wind turbine is more than double the size of the onshore wind turbine. This is again the map of resources for the US, for solar and for wind. So you can see that the dark colors correspond to the highest availability, resource availability, and therefore in the places where you have, and also in both coasts where you have most of the wind resources, and in the case of the solar, the lowest or the southern part of the US is where you have the resources. This corresponds to solar panels installed in the US, and this is again a map corresponding to where you can see the resources corresponding to any location. In particular, I have extracted the installation of the availability of solar and wind in Massachusetts. Here you have the offshore wind areas, okay? So you have here Boston is here, and you see these are the areas in the sea where you can install some offshore wind farms, okay? Some of them are developed and some of them are still not developed, okay? And on the other hand, you also see these areas, red areas, where you can develop offshore wind farms. I'm going to skip this. This is a video, okay, specifically in order to see which are the two features of this control center for renewable energy, of renewables energy. So there is a huge control center for dealing with all the kind of technologies, okay? But besides that, there is a control center only for renewable generation, okay? And there are two things that are mainly mainly targeting this center. One is observability, okay? We may have 10,000, 20,000 of wind turbines. So we need to take care or to observe every turbine in particular, or some of them aggregated, in order to see in real time which is the production made by each wind turbine of each group of turbines, wind farms, okay? And the other is controllability. If we have excess of generation, we need to send a signal and tell the turbine, stop, don't produce anymore for that hour, for some period, because your electricity cannot be absorbed by the system, okay? So these two kind of messages oriented to real time are key in order to integrate as much renewables as possible. This is what we did in Spain long time ago, some time ago. Okay, so in 2010 we started with 23 control centers in the different companies that were dealing with the main control center of the ISO, of the Spanish system operator. Okay, and nowadays there are 39 control centers providing that information to the main one. Okay, so instead of dealing with individual turbines, we are able to aggregate those wind farms in control centers, and this control center is sending the information to the main one. Okay, so this kind of hierarchy in the control centers has been also key in integrating renewables. Here we have some information about the wind farms in Spain. We don't have offshore wind farms, okay, because the marine platform is very deep, so we cannot. It's very expensive to locate offshore wind farms around Spain, but we have a lot of wind farms onshore. This corresponds to solar power plants. We have plenty of solar power plants. See the sizes, the biggest sizes corresponds to these big circles in the southern part of Spain. Okay, for those of you, we are at the same, more or less at the same latitude than Boston. Okay, so Boston, New York is located where we are in Europe. This corresponds to CSP, so solar thermal production, that is also our main power plants located in the southern part of Spain. These are the solar power plants, okay? And that corresponds to also to, again, to the same map where you can locate the different installations in Spain. This is the installed capacity for the latest years for wind and for solar, okay, in Spain. So nowadays we have 33 gigawatts of wind and 48 gigawatts of solar, okay? The blue ones corresponds to accumulated capacity, and the red one corresponds to the installed capacity on every year, okay? So we started installing a lot, okay, and then happened the crisis. The crisis lasted until 2020, okay, and then we started again installing additional wind generation, okay. Now we have 33 gigawatts, and in the case of the solar, so we installed long time ago, again before the crisis, then the crisis came, and then we have started nowadays to install again a huge amount, and we have reached 48,000 megawatts. Our peak is 44, okay? So we have as much, the solar production is higher than the peak. Of course, always the solar cannot supply the full demand because we don't have sun or solar production at night. Which is the share of the demand being provided by the wind production and by the wind generation? Around 25, okay? So you see that we have reached around 25% of the share that is being produced by the wind generation. This is the profile for the different years and for the different months, okay? So these are the 12 months, and each color corresponds to a year, okay? So we see that we don't have too much wind in the summer, July, August. We have windy end of the winter or spring, and also we have windy months in November, okay? And this profile is, let's say, consistent with any other, or probably many other northern hemisphere countries, okay? And this is the profile for the 24 hours a day, okay? This is 24, and therefore, given that we have a lot of wind farms located close to the sea, in the mountains, close to some big rivers, okay, we have a lot of regimes for wind blowing, and therefore the aggregation of all these wind farms means that there is no special pattern in the production, in the hourly production of the wind power in Spain, okay? This is the same kind of profile at the European scale, okay? So the 12 months, and this is a box plot without the, the streams, okay? So the box plot of the production at the European scale for the different months. So again, in the middle of the year, in the summer, the wind production decreases, and in winter and fall and spring is where there's a lot of wind production. This is the uncertainty from one year to the other. Okay, uncertainty from one year to the other. So you see here, for example, is since 1990 up to today, okay, and the share or the capacity factor of all the wind production. The capacity factor, remember, that means the production, the real production in that year divided by the maximum, in theory, production capability, okay? That will be the capacity times the 8,700 hours, okay? So you can see that along the year, we may have uncertainty. This is seen in this profile, okay? We have seen a lot of variation for a certain month, for example, for March, along the different years. However, in the full scale of a year, we don't have too much variation, only plus minus 4%, or plus minus 2%. So maybe it's blowing today or tomorrow, maybe it's blowing in March or in April, but at the end of the year, we can count with more or less the same amount of energy coming from wind if we are able to store them, to store it, okay? So if we are not able to keep the excess of production in some month safe somewhere, we will lost, okay? So that is why storage hydro, for example, is a good way to store the energy. And here we have more or less the same, but expressed in operation hours at full capacity. So basically, is the wind power in Spain is producing 2,000 hours out of 8,700 at full capacity, the equivalent in energy of that amount. How much is the, for example, the capacity factor of an offshore wind farm? This is onshore. Around 40%. So basically, if you put a wind turbine offshore, you are going to get more wind and therefore more energy, and the ratio of that is 40%. So maybe 150 or 200% more than if you put an onshore wind farm, okay? So that means that we can integrate a lot of renewable generation if we are able to either export or import from neighbors, if we have a strong network connection, or if we have a storage capability that nowadays basically is based on hydro generation, on hydro storage, okay, huge reservoirs. So for example, Hydro-Quebec is providing this kind of storage capability for this part of the US. Okay, why? Because they have a huge storage capability, huge hydros, and therefore they can export or import or keep that energy that can be if you have more than needed. Now we are going to see which is the impact of the uncertainty in the long, medium, and long term, short term, and real time.
You have the installation of storage solution compared to how the penetration of renewable increased over the year, what Spain did.
So if you tell me about the particular case of Spain, the specific case of Spain, we have not increased until now the hydro generation. We have had exactly the same for the last 15 or 20 years hydro generation, hydro availability. So it's just a question of being used differently. So what you asked previously to Javier, nowadays on every day, let's say in the morning and in the afternoon, the hydro units are generating, and in the middle of the day, given that we always have the duck curve, they are pumping. So they consume in the middle of the day when there is a huge solar production, and they produce in the morning, in the afternoon. Okay, so even stronger than the. This is the type of histogram or PDF probability density function. Okay, regarding the wind. So the main message are in the black box in the boxes. So we have 100% installed capacity. However, we have never go beyond 76%. So not always the wind is blowing simultaneously in all the wind farms. Okay, so the simultaneity is 76%. Beyond that, 5% of the installed capacity is exceeded always. So there is no calm on all the countries simultaneously. So at least we can count with, let's say, 5% of the installed capacity. That is not too much. I mean, and the mean value, more or less the capacity factor is 25%. These are the aggregated curve for hourly on top and for daily before. Okay, so the production of the wind order from the highest to the lowest. So in 1 hour, we have reached 88% of the total demand for a particular hour in some of the historical data. The historical data of the last 10 years or 11 years, that corresponds. On a daily basis, we have reached 70% of the demand produced by wind generation. Okay, and the lowest production, so for example, is only 4% of the hours we have produced less than 5% of the hourly demand. So there can be days or hours with very huge wind production or hours with very low wind production. This is another share. This is the penetration of renewable. We are talking about solar and wind. So we have reached, let's say, between them something close to 40%. And this is the different colors represent how many hours we are reaching or we are producing more than a certain percentage of the demand. Okay, and you can see that there are few hours where we exceed a lot of renewable generation is being satisfied by solar. Sorry, a lot of the demand, 90% of the demand is being satisfied by solar and wind. This is between 70 and 80% of the demand is satisfied by solar and wind, and so on. Okay, so we have different. This is the blackout, not to mention. We have a blackout due to control voltage problem in April the 28th of the previous year. Okay. Correlation between demand and wind production. No correlation at all. Okay, no correlation at all. Wind is blowing when it wants, and demand has the typical profile corresponding to human activity. No correlation with the CSP. Okay, no correlation with the solar production. No correlation with the photovoltaics. Okay, so what that means? That if we are, for example, these days, we are having probably here a huge demand consumption. Why? Due to the winter, due to the storm. Okay, can we trust that we will have wind available or solar available? Not at all. Okay, not at all. So that is the three messages. Which technology has been sacrificed in order to introduce solar and wind? CCGTs. CCGTs. You see here that up to 2010, the number of hours of the CCGT production was around 3,000 hours per year. Since then, due to the increase in the penetration of renewables, they have decreased to half of them, okay? So 1,500. So if we are increasing the penetration of renewables, some technology will reduce its production.
Is there a correlation of solar plus wind demand?
No. There is only a minor correlation in CSP. We have 2,500 megawatts. Half of them have a storage capability, so they can extend beyond the sunset. They can extend the electricity production until the first few hours of the following day. Okay. So we have to prepare the system for no wind, no solar availability. Okay, and that requires what is called here backup units. Backup units here. Okay, so some units must be always available when there is no wind and there is no sun. Impact in the short term. So this will be a typical day. This will be solar production, and you see that in the middle of the day you need to export or to consume electricity in order to absorb as much as possible of this solar production. Okay, so therefore you need flexible units that are able to absorb that variation. This is a particular case, solar eclipse, okay, where naturally all the solar generation goes down, okay, because there is this solar eclipse, and you must absorb this variability. These were the ramps that were expected at the Germany level, in Germany. So beyond, let's say, 21,000 megawatts per hour. Huge amount of variation due to this solar eclipse, okay? It's like the half of the demand of Spain. That was the expectation, and that was the reality, okay? The reality, they observed 8,000 megawatts per hour ramp and 7,500 megawatts hour per ramp for increasing, coming the solar eclipse and leaving the solar eclipse, okay? So given that this is natural and you can know in advance, you can try to control this variability by providing some measures. The same happened a time ago in California in 2021, okay? You have another minor modification, but there was this amount of megawatts from utility scale solar that was changing or reducing its production. So again, this natural phenomena can be controlled or can be, but you need to protect the system and to absorb this variability that is not natural. Well, it's natural, but it's not a common day, okay? But you must be prepared for that, which is the consequence of a higher penetration of renewables. Prices decrease, okay? Prices decrease. You see, in particular, 2 days here, you see that the scale is different. This is April, and this is November. In November, like here, we have colder, higher demand, and therefore prices are higher. So we reach here 175, while here we are having 120 in this scale. So the increase of solar and wind production means that the electricity prices at the end are going to decrease. This is
summer, there are times that the minimum.
No, this is 30 days per month, so that corresponds to days.
There are times that the minimum price is 0.
Yeah, so it can be. So spring corresponds to high hydro generation, typically high wind production, and not the highest, but high solar production. That is why that may happen. And even we can even include the Easter vacation period. So all of these 3 causes or can cause prices going to zero. Prices going to negative values. So this is frequency of negative electricity prices in 2022 in the USA. So, and you see that more than 20% of the time you may have negative prices in the middle of the US due to this excess of generation. So, means that if you are being subsidized, you are able to lose money because on the other hand you are receiving a subsidy from outside and therefore you are able to absorb negative prices. This is in the case of solar or wind farms. Okay? In the case of a thermal generator, you are spending a lot of money, you need to stop and to start up again, and therefore you are able to lose money for some period of time in order to avoid this additional cost. Okay? So the message here is, in the short term, that will be the typical period for the unit commitment, we need to have flexible unit. Flexible unit means gas turbines, combined cycle gas turbines, or hydro units in general, okay, that are able to absorb this variation of the wind production or solar production along the day, along the week. Impact in the short term. How many errors, how much is the error we are observing for predicting the wind, okay? Now we must predict the wind for tomorrow because we are clearing now, right now, we are clearing the market for tomorrow in the day ahead markets, okay? So how much is the error? This on one hand is the decrease along the time, okay? So the worse, always we are improving the technology, the forecasting technology, and therefore that curves decrease. And here we are saying that is from now 6, 3, 12, 24 hours in advance, okay? And the expectation, the errors are like this. So we may expect 2% of error in wind production, okay? For the next, let's say, 6 hours. For the next 24 hours, we may have 2.5% of error. So the errors increase when you move away from real time, from now, okay? And also, that's all I wanted to say. Okay, this is for wind. This is for solar PV. We have more or less the same error. And this is for the solar CSP, okay? This is depending on how many wind farms you are aggregating, okay? So that errors decrease because you are aggregating large areas. It's difficult to predict a single wind farm, it's less difficult to predict 100 wind farms, and it's less difficult to predict the whole system, the whole country or the whole state wind farms, okay? So that's why aggregating the wind production is easier to predict at a whole scale. Given that you are not able to integrate all the generation, you must curtail. Curtail means not to produce, sending a signal, not to produce a certain wind farm or a certain solar PV farm, okay? So this is renewable curtailment for the different countries. We are these ones. So we have started to curtail recently, okay? But there are other countries where there is more curtailment than that. We can even follow month by month the curtailment made in the Spanish system. I'm going to skip that also. Curtailment in California. This is solar curtailment and wind curtailment. Solar curtailment and wind, you see that the wind is much smaller, but you see at the same time that the solar curtailment is increasing a lot, reaching values of 500, 700 gigawatts hour. Okay? Why? Because we are able not to integrate all the generation, the solar generation available. This is the same for the southwest power pool, okay? They are again increasing along the time, and most of this is for wind curtailment. It has said that it has increased by 37 times the original curtailments. How we protect the system against the error? By means of the operating reserves. So Javier has mentioned what is called upward and downward spinning reserve. Spinning is the word used in the US. In Europe, we use operating reserve, and we distinguish between automatic, manual, etc. What is that? Basically, we need to produce a certain amount of energy, but at the same time provide power, not producing electricity, that we are able to increase or decrease. If we have, for example, a 400 megawatts CCGT, we can produce 300 megawatts, and therefore, if required, in seconds, we are able to increase to 100 more, or in seconds, we are able to decrease to 100 less, okay? Assuming that the minimum stable load is 200 megawatts. So this power that is offered to the operating reserve market allows us to absorb the uncertainty, the error in the wind production or in the solar production. We have, let's say, a wind farm, we predicted and we sent that bid to the market, that was clear, and then we are producing more than expected. Therefore, any other unit must decrease its production in order to balance generation and demand, or if we are producing less, any other unit must increase its production. This power availability in order to increase or decrease production is called operating reserve or spinning reserve, because it's provided by machines, by generating units that are rotating. That's why it's called operating reserve. This market is clear just after the day-ahead market. Okay, what changes? I'm going to start with the stochastic unit commitment. I'm going 10 minutes later. So the stochastic unit commitments tries to include uncertainty. In this prototype, I'm only including uncertainty regarding wind production. Okay, so we don't know now which is going to be the wind product to be produced tomorrow, and we are providing some scenarios, okay? We can call calm scenario, windy scenario, and average scenario. Can be 3 scenarios or can be 300 scenarios, okay? And typically, there will be variation, and when tomorrow comes, okay, maybe the real production is different from these 3 scenarios. However, we want to consider 3 scenarios, let's say, in order to determine the best commitment decisions that we must take today for the units to be committed tomorrow. Okay? So this is what we call a stochastic unit commitment. We must take a unique set of commitment decisions, but taking into account the uncertainty corresponding to wind production for tomorrow. What changes? We have introduced the expectation, the expected operation cost. Okay, why? Because we are dealing with 3 scenarios, each one with, in theory, one probability, a different probability. We will introduce this omega corresponding to scenarios. Omega will be scenario 1, scenario 2, and scenario 3. That will be the profile corresponding to the demand. We are considering here 5 days, okay? In the model, we consider a week, 7 days, no, a month, no, a day, a week, okay? We introduce 3 scenarios. We can call this windy, we can call this, let's say, calm, and this average, okay? the profile that will be the profile for the 24 hours, the expected 3 scenarios that the forecasting people has provided us in order to take them into account in our model. This is the same kind of formulation used by Javier, the same kind of information used by Javier. This is the mathematical problem, schematically presented. So here we have what are called first stage decisions. So they correspond to the unique commitment, startup and shutdown decisions of the, let's say, thermal units corresponding to the 24 hours of tomorrow. Okay? And these are the second stage decisions that will be the generation, the generating power of every generating unit for, here we have, let's say, 7 scenarios. I have already mentioned 3, okay? Can be 7, can be 3, can be 10, okay? And that will be the production for every generating unit for every 24, for each hour of the 24 hours of tomorrow, okay? So that means that basically we are creating a model that in this particular case will be 7 times the size of the previous deterministic model. If we are considering 3 scenarios, basically we are multiplying by 3 the size of the model. We have a single commitment decision unit, commitment decision for a generating unit. Here we have 7 potential, 7 generations for a unit, okay? So we are multiplying the difficulty in solving this kind of problem. What we consider uncertain was in this particular case the IG, intermittent generation, okay? We are considering for the 24 hours, we are considering which is the output that depends on the scenario, okay? For the calm scenario, we are considering a low profile for wind production, for the average scenario, something in the middle, and from the windy scenario, something on top. From a mathematical point of view, we have added the omega. That means that we are multiplying by the number of scenarios this variable. So the power produced by each thermal unit on every hour depends on the scenario. We are adapting the production of the unit to the corresponding scenario. If we have more wind, we will produce less with the thermal units. If we have higher wind, we will produce more. Okay? Therefore, the set of commitment decisions is unique. They do not depend on a scenario, on omega. However, the production is adapted to the corresponding wind. Here we have introduced the expected value, okay? Why? Because we have different scenarios with different probabilities. So we are considering, for example, 3 scenarios, one with 30% of probability, another one with 50% of probability, and the third one with 20% of probability. Therefore, we consider these probabilities in our decision model, and we protect the operation of the system with respect to this uncertainty. You have again 2 possibilities for unit commitment. I'm going to this. So you can again at least try to run it. You can find the model in this GitHub link, okay? It's just GitHub open SDUC, stochastic daily unit commitment. I have used another type of installation different from Javier, okay? So first, if you don't have mounted your drive, you can mount, okay, these first 2 instructions for mounting your Google Drive, okay? Then go to this GitHub, and download from code download zip, you are downloading all the GitHub. Okay. Ah. And then you have to download. It's not a Jupyter notebook, it's directly code in Python. It's called OpenSDUK_main init, and also a folder where this 16 generators case study is included. Okay, so you must download the two Python files, the init and the main one. Okay, you must download the folder 16G, and in that folder you have the CSV corresponding to the input data of the model. If you have been able to do that, you can move then to your drive in Google Colab. You can drag and drop in Google Colab, in your drive in Google Colab, and then the way to model will be to create a notebook or code, where is put plus code, opens a small window, and then in there you can put, ¿cómo se dice admiración? Exclamation mark, Python, and then the folder where the open main is contained. Have you been able to do it? Yes. Okay. If you run it, it will ask you about the name of the case study, that by default is 16G, the name of the solver, that by default is hikes, and you want results or not. Just press enter, no need to modify anything, and it will take some time, few seconds to run it, and you will have the results in the 16G folder. They will be called OD result and then any name. Okay, and you have some plots there also. Voy a tomarme 5 minutos más de mi tiempo. It's a CSV file and a PNG. So there are two plots. You must open the 16G file, and you will find there several result CSV files and also two graphs, two plots. So it's essentially something similar to what Javier has provided, but instead of being in some blocks in a Jupyter notebook, it's all the things all together in a single Python file. And the graphs are plotted there, but not, let's say, interactive as in the Jupyter notebook. Who has been able to run it? 2, 3, 4, 5 of you. 1? the have you s- are you opening the 16G file folder
I'm running it on the local, though. I'm not running it on the.
in Google Colab?
No, I'm running it on the local. It runs. It doesn't give any error.
Okay.
But then when I go to 16G, there is no result.
And you have ended with academic license, something like that?
Yeah.
Must be somewhere. So in theory, it's reading from this, is reading the input data from this folder and writing also in this folder. This is the idea. So we can talk afterwards. Let me continue and provide you with some analysis, okay? Why we are dealing with this stochastic, which is what justifies this stochastic unit commitment. The uncertainty. The uncertainty. What we have done, we have created, in this particular case study, we have created 3 scenarios corresponding to win, possible generation, okay, or potential generation, and we are taking them into account simultaneously in the stochastic unit commitment. However, we also can convert this model that is stochastic in a deterministic one. How we can convert this stochastic model in a deterministic one? How? Okay, we can take the mean, or we can just disregard the probabilities. So if we assign probability 1 to the windy scenario, then we are running the windy scenario. If we assign probability 1 to the calm scenario, then we are running the calm scenario. If we assign probability 1 to the mean scenario or to the average scenario, we are converting the model into something deterministic, okay? So the reason for doing that is these are, once we have run the model, we obtain things like that, okay? So scenario 1, scenario 2, and scenario 3, and short run marginal cost for the 3 scenarios. The windy scenario will have higher wind production. The calm scenario will have lower wind production, and therefore we observe differences in these values, okay? Wind production is this dark blue, and you can see the differences between the 3 ones, okay? The total demand will be the same, however, the dark blue profile will be different depending on the scenario, okay? So what happens from the point of view of the commitment decisions? Remember, in a unit commitment, we are only interested in providing right now the commitment decisions for the thermal generating units for tomorrow, okay? If we use, instead of a stochastic problem, we use just one scenario, we obtain this kind of, this is the total number of committed units if we consider only scenario 1. This is the total number of committed units if we consider only scenario 2. And this is the total number of committed units if we consider only scenario 3. If these three profiles are different, mean that if we take a deterministic model and we assume that we know which wind scenario is going to happen, then we will obtain different commitment decisions, okay? So that means that our stochastic unit commitment is protecting decision, is hedging our decision against this uncertainty. So what will happen if we consider the stochastic with the scenario 3? That will be the commitment decisions. What will be the result if we consider the deterministic scenario called the mean scenario that will be the weighted mean production with the corresponding probability, this one, okay? So you have seen the differences in the commitment decisions that are the main ones we want to take with this type of model, okay? If we assume perfect knowledge about the wind production for tomorrow, depending on the scenario, or in the mean scenario, or with respect to the stochastic unit commitment, okay? So by means of this, we are able to show which is the relevance of showing the value of the stochasticity for this unit commitment problem, okay? From a numerical point of view, we see here, for example, different changes depending on the scenario. We have 3 deterministic scenarios, scenario 1, scenario 2, scenario 4, scenario 1, 2, and 3, okay? Then another deterministic scenario that is called mean scenario with the weighted probability of the wind production, and the 5th one that will be the stochastic. And we can see that there are differences in the objective function, in the production of the different technologies, and so on. So in theory, we are saying that the stochastic solution, at the end, when doing this thing many times, we are able to take advantage of that stochasticity being included in our stochastic unit commitment model. That is all I wanted to say. Now we can stop for 5 minutes, and then I will continue myself with another topic for another hour, for another 55 minutes. Okay? Thank you. Let's rest for 2, 3 minutes, 4 minutes.